In this explainer, we're diving into the research of Clovis Rocha Sampaio Jr., and his work puts forward a really radical idea that pi's irrationality isn't some absolute fact, but just a product of the way we've been looking at it all this time.
So, here's the big idea, the core of this new vision. Pi's nature isn't absolute. Instead, the author proposes that its characteristics are conditional. They depend completely on the geometric lens we're using to look at the circle in the first place. And this slide really shows you what that means. It's such a powerful visual contrast. On the left, you've got our traditional Euclidean view, where everything can seem pretty complex. But on the right, inside what the author calls the isometric plane, a hidden order just appears. You can think of it like a different kind of geometric grid, one where the main idea is that pi's chaotic digits can actually line up into a predictable, repeating structure. So you might be asking, how is a new perspective like this even possible after thousands of years of math? Well, the answer really comes down to technology. This research goes way beyond the historical limits of a simple ruler and compass. It uses the power of modern dynamic math software called GeoGebra, which lets you get a level of precision and visualization that was just totally unimaginable to earlier mathematicians.
All right, so now we've got this new framework and a new set of tools. So, the investigation starts to uncover some really interesting clues that back up this hypothesis. And the trail of evidence actually begins with another very famous mathematical constant.
The first key piece of evidence here involves the square root of 3. Now, inside this isometric framework, the author doesn't use it as an irrational number. Instead, it's used as a super precise tool to define the circle's dimensions. And this specific choice is argued to be the key that unlocks what he calls rational divisions, which are basically perfectly predictable and repeating segments inside the circle.
And this table here shows you the next step. By looking at fundamental trig functions like sine and cosine through this new lens, the research generates these tables of values. Now, the argument is that these are not just close approximations. No, the claim is that they are exact, perfectly rational, and periodic infinite numbers, showing an underlying predictability where we've only ever seen irrationality before.
And get this re-examination even extends to the classic method of Archimedes. By using GeoGebra to analyze polygons inscribed inside a circle, the author sees a consistent pattern of what are described as rational divisions. This data is then used to suggest that the ratio of circumference to diameter, pi itself, isn't an irrational constant, but the limit of a series of perfectly rational and predictable divisions.
Okay, so to really make this logical framework stand up, the author has to challenge another huge mathematical cornerstone. Most of us have probably seen the standard proof that the repeating decimal, 0.999 ... is mathematically identical to the number 1. But this research, it presents a counter-argument.
Using GeoGebra's high-precision calculator, the author points to a result from the software that seems to challenge that identity. You can see it here. The software calculates 1 divided by 3 and gets a value that ends in .33347. And when that's multiplied by 3 within the program, it resolves to exactly 1. The author presents this as computational evidence for a tiny, infinitesimal difference that standard proofs might be overlooking. It's a necessary step to build the logical case for pi's potential rationality.
So let's pull all these threads together. We've got the isometric plane, the trigonometric values, the polygon divisions, and this re-examination of infinite series. All of these pieces are building towards a single, unifying, and pretty revolutionary hypothesis.
This new hypothesis needs a whole new category of number. So the author proposes the rational periodic infinite number. And it's defined as a constant that can be expressed as a sequence of infinite rational ratios, all of them derived from precise and repetitive geometric relationships. And here it is. This is the culmination of the entire investigation. The research proposes a direct challenge to centuries of mathematical consensus that pi and other fundamental constants like the square root of 2 and the square root of 3 are not irrational. The argument is that they are in fact members of this newly proposed class of rational periodic infinite numbers, meaning they have a hidden, repeating order. So why does any of this matter outside of pure mathematics? Well, because pi is literally woven into the fabric of science. The equations that describe space-time and cosmology, wave functions in quantum physics, the limits of chaos theory, they all rely on pi. If you redefined its fundamental nature, from a symbol of randomness to one of hidden order, well, that could change our models of the universe and open up brand new paths in fields like quantum computing. This is obviously a profound challenge to established thought,
And to really understand its place, we need to see it not just as a mathematical claim, but as a new chapter in a very, very old story.
I mean, this research is building on a 4,000-year saga, from the Babylonians' first approximations to the Egyptians to the absolute genius of Archimedes. The hunt for pi has always been a story about humanity using the best tools we have at the time. This timeline positions the work of Clovis Sampaio Jr. as that next step, using the dynamic software of today to ask questions that were once simply unimaginable. In the end, this research isn't being presented as some final, definitive answer. It's offered as a contribution to our endless search for knowledge. It asks a really powerful question. Could a simple shift in perspective reveal an underlying order in what we have always believed to be infinite chaos? And right there, in that question, lies the very spirit of discovery. Thanks so much for watching all the way through. And hey, don't forget to subscribe to keep getting more deep dives like this one.